Let's start from the previous class. In the previous class, we see about the evaluation technique of the classification models. So, in order to decide that which algorithms we select, we should evaluate the performance in different ways. So from that one of the measurement techniques for the performance of the classification model is measuring accuracy. So the goal of this measuring accuracy is just we want to measure the effectiveness of the classification algorithm just by using the training data set, and then we can build the model, and finally in order to test or measure the accuracy of that performance model, we use a new test data, or using the training data set, we can test the performance of the model, and then if that accuracy is acceptable, we can implement or deploy that model for the application in different areas. So this one is actually that is used to implement for the real accuracy of the model and the one indication. Actually, this in order to measure the accuracy, just when we train the models, just we can split the data into the training set and the test sets. So the training set is used as a training for our data, and then half of or maybe 20% or 30% of the data can be kept, and then we can use as a test data. So by using that 20 or 30% of the data, we can test the performance, and then we can calculate the accuracy of the model. So this leads to the potential errors in estimating the real classification rate, because the half we hold for the testing may be very different that half we used for the training. So when you use like some half of the data, once the model is just trained like based on 80% of the data, and then when you test 20% of the data, that test data is just learned from or based on the training data, just estimate the prediction, and then we can compare the actual versus the predicted one. Then that difference is, or the difference between the actual and the predicted value is just showing the accuracy of the model. In order to calculate the accuracy of the model, it counts just by using a test data. Counts test recorded that are correctly or accurately classified, and incorrectly, or that is the error parts predicted by the classification model. So just by splitting some data as a test data, we can measure that one, and we can compare which one is correctly classified and which one is incorrectly classified. So the correctly one is just by compare and contrast with the actual one, or that means from the real data. In the training data, we have already labeled data. So from that labeled data, we know that some of the 20% data that keep means that includes with the target data. And then from the test data, there is also a prediction result by the model. So by comparing the predicted one with the actual one, we can identify that how many of the data is correctly classified and how many is like incorrectly classified. So in order to determine, or in order to show the accuracy of that the classification models, the one technique that we use to show the performance is the confusion matrix. So the confusion matrix showed that the table between the actual classes and the predicted classes. So the actual class means actually that is the already known, or the ground truth, the values. For instance, in this case, we have two classes. The class is the indicators yes and no, and then there is a predicted class that is predicted by the proposed models. So there is also the class yes and class no. So in both cases, actually the class is just two for this case. So let's say, for example, the class S and the class here, this one the predicted, and this one is the actual one. And then if the predicted and the actual is become the same, like for example here F11, just the data name, so we can say this one is accurately classified or correctly classified. That means because here also yes in the actual one, in the predicted also yes, that means that this data is correctly classified based on the proposed model. When it comes to this one, the actual class is yes, but the predicted class is like no. So the model is predicted as no. So that is this, the red color, it showed that F10 means that is incorrectly classified. Also the second class, the actual class is no, and the predicted one is yes. So this one also, that indicates the incorrectly classified one. When it comes to this one, the actual class is no, the predicted class also is said that is also no. That means the actual one and the predicted one is the same. So this one is, we say that, correctly classified. So based on this table, this confusion matrix, it showed that F11 and F00 is number of test samples with the label correctly predicted, while F01 and F10 is the number of the test samples that is incorrectly predicted. So from this one, in order to calculate the accuracy based on this table or confusion matrix, accuracy is equal to the number of correctly prediction over the total number of predictions. That means from this one, the number of correctly prediction is F11 plus F00, this one, over the total number of the test samples. That means this one plus this one plus this one plus this one. So the total one. So just accuracy is just easy to calculate which data is accurately or correctly predicted. Because of that one, just we can calculate based on this one. So actually when we develop the model, this accuracy is automatically calculated, or we can just assign by codes, and is actually by differentiating between the actual one and the predicted one, the accuracy is done by in the code, but just that accuracy is calculated based on these equations. So this table also showed that, like the actual class and the predicted class. So in the confusion matrix, we can say that the true positive, the false negative, false positive, and true negative. That means actually true positive means from the this class, from this one, for example, in the actual class, in the predicted class is like the same is the class is yes, that is because the class that indicates yes, we can say that the true positive. For example, in this case, the actual class is no and the predicted class is yes. So actually there is an error, but still that we can say that false positive because the actual one is like no in this case. The other one is here, the actual class is yes, and but the predicted class is no. So we can say that false negatives because this the class one based on the prediction one. This one it showed that 10 or true negative means the actual is also no, and also the predicted is no, which is the class is correctly classified, which indicates that true, but the result, because this one is no, we can say that true negative. So in total, in order to calculate the accuracy, we can take this diagonal, the true positive and true negative, that indicates the true, that is correctly classified. It shows that over the total number of this one, that is both the positive and negative. Positive and negative indicate that this one is positive, negative, positive. Negative means that includes all the four datas. If the number of the data set included, this one is actually just 4 because of here the test data is 4. However, if the number of the test data set is 10, that means that the same like the number of the data, we can just calculate the correctly classified over the total number of the test data. This is the way how we calculate the accuracy. On the same way, we can calculate also the error. So error is like calculated by the number of wrong predictions over the total number of the prediction. So from this one, we can say that F01 and F10 is incorrectly classified. That means F10 plus F01, this one, over all the data set like the above one. So the total number of this one. The same case, so when it comes to in the error is like the reverse of this one, because it's like false positive and false negative, that indicate the wrong classification. So this one over the total number, the whole, the red circle, that one. So this color shows that this diagonal, and this one is indicating the red colors, that means the whole data. So the error is the same. In the other case, actually, if we know the error the error, we can calculate the accuracy simply, or if we know the accuracy, we can know the error by simple, because error is equal to 1 minus the total number of the accuracy, or from the 100%. If we say that the accuracy is 100%, 90%, that means the error is 100 minus the accuracy. So just we can simply by minus from 100, we can know also the accuracy from that one. So using this type of equations, we can calculate that the accuracy, and then we can know that how the model, the performance, and then based on this performance, if the accuracy is like maybe 90%, 85%, and like that one, we can say that the model is good and well trained and is ready to implement in the real implementations to test and see all new test data. This is the one way of the evaluation techniques that is called accuracy or the confusion matrix. Another evaluation mechanisms for evaluation of the classification model is the precision and recall. When we say that precision, this one precision is the fraction of the positive predictions that are the correct. So precision is equal to true positive, which is the true positive one that is classified as like here, and then over true positive plus false positive only from this one. So based on the prediction, the positive prediction that are correct. So we can take like true positive over, based on the prediction, we can say just consider the positive prediction, that's considered the yes. So that is why true positive, this one over true positive plus false positive. While in the recall, the fraction of positive instances that are identified. So this one is true positive over true positive and plus false negatives. So this one is actually that indicates the positive from the actual one. So that this is the way to calculate also the precision and recall. That's different from the accuracy. So based on this one, we should consider that if it's type of like multi-class classifications, because in the accuracy, in the precision, and in the recall, we can say that just the true positive 1 plus true positive 2 plus true positive 3, it depends on the class. That means this one is just for binary class. So if it's multi-class, like let's say 4 class, so true positive 1 plus true positive 2 plus true positive 3 plus true positive 4. So it indicates, let's say for example, this one is the 4 class, so we can include that a true positive 1, true positive 2, and true positive 3, true positive 4, and then we can also increase depends on the number of the class. And also the fraction one is true positive 1 plus true positive 2 and false positive 1, false positive 2, and then like true positive 3, we can include the same case because this one include that the whole. So totally the divide one is include depends on the total number of the test data. So depends on that one, we can calculate that, the precision and the recall values, and also in the accuracy, the same case. In the accuracy part, if the number of the data can increases, even in the class number, in the multi-class, we can calculate that F11 plus F00 plus like the other classes. And then the divide one is that includes the total number of the class, that indicates the total number of the test samples. So based on this one, we can calculate the evaluation techniques in the classification models. So this the read one, it just showed that the total number that include on this one. So for example, if it's 4, you can include on this one, so don't confuse. So you can just check it by accuracy or either precision and recall. Actually mostly this the precision, recall, and accuracy in classification, this type of especially precision, recall, F1 measure is the most common measurement techniques for the classification algorithms, and accuracy is most commonly especially for the regression one, because precision, recall, and then the other one which can say that F1 measure is the most commonly used type of evaluation techniques to evaluate the performance. So always once you select the model and after train that model, in order to say that that model is good and our just goal is achieved, means depends on the performance of by evaluating using this type of evaluation techniques. So the other mostly used type of evaluation technique for classification model is F1 measure. F1 measure is like also the good technique, measurement techniques, because of it's like combining the measure of the precision and the recall trade-off here. So in this case, just F1 measure, like it's equal to 2 over 1 of the positive and 1 of the R1, or the precision and the recall 1. This P indicates the precision and R indicates the recall 1. So that means 2 times precision times recall over precision plus recall. So this is just by combining the precision and the recall values, and which is indicated that like the average. So because of this one, F1 measures as which is the average precision and recalls are just weightly or weightly evenly by calculating or combining these two measures, F1 measure also like the one measurement technique, to get like the average of the precision and the recall. So just this one, it depends on that one. All this one, the precision and recall and all the accuracy is calculated by, it depends on the predicted and the actual class. Okay, we already seen that what is classification mode is. So next, let's try to see about some of the example of the classification algorithms. Like there are different number of types of the classification algorithms or classified algorithms. So the first one is k-nearest neighbor, or we say that KNN, and support vector machines, decision tree, Navi Bayesian network, random forest, neural network, and there are a lot of classifier algorithms for classifying the data. That is like, so this type of algorithm, we can say that type of supervised learning, because a classification is a type of supervised algorithms. So I think we cannot go in detail about each algorithms, but just we can see like an example of about like the first two one, and maybe the other one is just try to dig and search and read about that one. So I will show you that about the example of how the k-nearest neighbor networks can work. So when you say that nearest neighbor classifier or KNN, this nearest neighbor classifier is like for an algorithm that works for a test data point, assign the class label of the nearest training data. So the working principle of this algorithm is like for testing data, assign the nearest neighbor data from the training one. So in order to determine the nearest neighbors, adapt the distance function to find the nearest neighbors. For example, from this example, we can say that this one is the training example from the class 1, and this is another training example from class 2. And then let's say, for example, this one is the test examples. So in order to determine that in which class this test sample is categorized, either in this class or in this class, we can determine by calculating the distance from here to this one, or the distance between this one and this one. So if the distance between this one and this one is nearer than the other one, that means this test data is classified into this class. That is, nearest neighbor is working like this one. So by calculate the distance to each data point in the training set and assign the class of the nearest data point, which is the minimum distance. In this case, just the only parameter that we need to define is the k numbers or the k values. For example, actually the only parameter that we need to define is, we say that k. So the k value is equal to 3. Let's say k value is equal to 3, like for this one. So if we say that the k value is equal to 3, means assign 3 nearest data for our test data. So the k value may be 3, or k value may be 2, or k value may be 1. It depends. So the only parameter that we need to adjust is then assign the k value in the training. So when you say that k is equal to 3, that means just let's say, for example, this plus sign is our test data and have two different classes, X is the one class of data, and this O is another class of data. So this plus is like the data, a test data. So in order to classify this data, the plus one, we need to just consider 3 nearest data. So for this data, the first nearest is this one, and the second nearest is this one, maybe the third is this one. So we should be circle 3 data, because we say that k is equal to 3. Here, 3 nearest neighbors. 3 nearest neighbor means k is equal to 3. So let's remove this one. So k is equal to 3 means just circulate or circle or select the 3 nearest data for our test data. So for this case, the test data is plus indicates test data. Our test data is the plus one. For this test data, when we pick 3 different data, the majority is like O indicates 2, and the X data, because total is 2 class based on this one. So that means based on this one, because we select the majority of 1, this test data should be categorized into the 0 O. This the shape. So this test data should be categorized in this one, because the majority is here is just 2. This one is majority than the second one. Also, I have another test data here. Based on this test data, first we should choose 3 data pointers that is nearest to this one, our test data. So from this one, like we say that this one is the nearest, this is the nearest, and this is the nearest. So based on the majority rule, this class is also categorized into this one. So let's say in this case, we have 2 classes. This one is like we say that class 1, and another one is X is class 2. So we have 2 classes. So the plus 1 is our test data. We say that this one is our test data. This one is our test data. So this data can be categorized into this one, because the majority one indicated that this data is the majority is indicating or like assigned for this one. So because of this one, just this test data is categorized into the O class, or we say that class 1. So the class of the text example is obtained by voting 3 closest pointers. That is the case. So k nearest neighbor means k nearest neighbor. K indicates that the number of the data pointers, and then just we can select that based on that number of nearest neighbors. So the working principle of this k is actually just no need to much training, just only assign the k values, and the accuracy generally improves with the more data. So when the data is like increasing, the accuracy also increasing. So matching is simple and fast. Actually, this is just a simple type of algorithm. Mostly it's better for just not for too much huge data, but it's because it's simple type of machine learning algorithms. So usually needed data in memory, but cannot be run off the disk. Just only have a memory to remember each data point. So when we just give a test data, that by checking from the memory, just compare the nearest of the data pointers and then decide which one is in which class our test data will be classified. So the only parameter that we need to assign in this one case is k, number of neighbors that represent. So this is the way that indicate. So this is actually, for example, a set of stored cases or the memory here. So just attributes here, and then there is a class here, because type of supervised learning, first we should know that the class of each attributes or data point is this one. So let's say, for example, in this one, we can say that, for example, this is the different attributes. The class actually, in this case, there are different type of class, A, B, C, 3 classes. So there is an attribute here. So that means next time we have an attribute here, like the same way to this one, but we don't know about the class. So that means in order to determine this one, we have an attribute here. Then finally, we need to know that the class for this one, we need to know the class of this attribute, or unseen case, which is the new test data. So this is, we have already the one pre-processed data that have attributes, a number of attribute 1, attribute 2, attribute n, and we know also the class, but we need to decide that the class of the unseen test data. So we know the attribute, but we don't know the class for this unseen data. So in order to determine this class, just we need to determine the class based on the nearest neighbors, only because KNN is just working based on this principle. So based on this, if we know that k value, first we can determine the k value. So based on that k value, let's say that if k is equal to 2, so just the data is determined that is nearest to the k value. So this k value that memorize the entire training data, because it's a memory, so we should be considered that the whole data. So perform classification only if attribute of test sample match one of the training samples exactly. So the other one is use closest samples that we already see. So this is the way, the principle. So to classify a test sample as a procedure, or the procedure is this one. The first one is computing the distance to sample in training test. So let's say this one is, the red one is test data, our new test data, like here. We can say that, for example, this one, our test data. So this table, let's say as an example. So in order to test this one from the two class, in this case have the two class, the one class is this one, and another class is this one. So just two class. So in order to determine, or in order to indicate that our class, here there is different ways. The one is the plus class, and the one is this one. So we have two different class. So this class 1 and another one class 2. So in order to determine this one, we can say that k is equal to 3, or k is equal to 2, or k is equal to 1. So we need to check that by changing or varying the k value, we can determine the best performance. So by varying the k value until we find the best accuracy. So identify the k nearest neighbors. Just we can determine k is equal to 3 for this case. So because of, we say that k is equal to 3, first pick the nearest 3 data for our test data, and then use class level of the nearest neighbors to determine the class level of test sample. That is by taking the majority vote. So because of this one, actually for this case, unfortunately, all the class is just only plus. So the class is easy to determine because almost all the 3 data point is similar. So it's like this data is classified into the plus class. But if, for example, this one is minus and the other one is plus, that is based on the majority vote, is like classified into the plus 1. This one also like in different ways. For example, in this case, just only when the k value is 1. When the k value is 1 means just for our test data, this x is our test data, so just pick one data point that is nearest to our test data. So based on this one is the class, or the test data is categorized or classified into minus class. When the number of the k value, so in this case, k is equal to 1, in this case k is equal to 3, and in this case k is equal to 3. In this one is k is equal to, and this case, because 3 nearest neighbor, these 3 represent the k value. So when the k value is 2, this one is our test data, x is the test data, so just pick 2 nearest neighbors for our test sample, and this one and this one is selected. So which is actually in this case is like the plus 1, but so because of this equal one, we should be based on the distance. Actually this one is the nearest one, so we should be calculate the distance. So the nearest one may be the winner one. And if this one is 3, when the k value is 3, that means this is test sample, and then select 3 different points, and then based on that the majority is in the plus class. So this is the way in the simple algorithm. So that is only needs to assign the k value. So for example, in this case, if works like a duck, quacks like a duck, and then it is probably a duck. So this is, for example, number of animals here. It looks like a duck training sample. This one is the animals, and this is the test sample. So according to k value, from which animal that looks more similar for this one, in order to categorize from this one. So to determine that, all this one is just calculating based on the similarity distances. So compute the distance here based on similarity. The distance is just only based on not that one, not a line distance, but like based on the similarity distance. So based on this one, the two one is just closest to the k value. So choose k of the nearest sample. That means this one and this one is more similar for this test samples by calculating the distance. So this is also the one procedure. For example, this for test data, which one is the similar one is working. When it's 3 nearest neighbor, just pick the 3 one and working. When this one is 5 nearest neighbors, just pick the 5 nearest one, and then use the majority vote to determine in which class that test data should be classified or assigned. So it's not actually this type of classifier. Maybe it's not like the type of learners. It's just, we can say that lazy learners. So does not build the models explicitly, and unlike eager learners such as decision tree, induction, and rule-based systems. It's not like for especially for complex data. Well, this type of classification algorithm may not be good, but still it's like working the good tasks. We say that actually in order to determine the nearest neighbors, we use like this type of distance calculation mechanisms. The one is Euclidean distance. So this one is the simplest and fast to compute. So in order to calculate the x and y, there is so the actual and the y one. So by calculating this one, the test data, and the actual one, I mean the training data. So by calculating this one, the difference between this one, we just calculate the distance, and then that means the smallest distance have the similarity. So if this distance is smaller than the other one, that means that test point is classified into that point. So by calculating this one, if the difference between x and y, this one point and this one another point, so if the distance is small, then that one is class, or the test data is categorized into this one. And the other one is the cosine distance. Also this one, just 1 times x times y over the absolute value of x and y. This is also another mechanism to that one, but the most common one to calculate this distance between the different points is like Euclidean distance is the most common one. There is also the Manhattan distance, that coordinate-wise distances to calculate on that one. So just the total summation of different points. So by using this calculation between the two different points, so this summation of because of have more than one point. So by calculating that one, just determine by using the Manhattan distances. So there are also other distance calculation mechanisms, but the most common one, or the simple one, is Euclidean distance, just the absolute value of the difference between the two points. Using that one, we can determine the distance between the different points and determine in which class that this sample should be classified. This is also another example just for the animals. Just this one is the test data. So in order to find which animals is more similar with this one, so find the k closest matches in the label data set. So like that one, if k is equal to 3 for votes for the cast, so we just pick that the three most similar animals for that one. So based on this one, actually just this one is an example that showed that this one is more similar on this one. So based on similarity, that distance is calculated based on similarity. So from the other one, because we just say k is equal to 3, that means we should be select 3 data points that is more similar to this one. If k is equal to 2, maybe only select this 2, only the maybe only this part. If k is equal to 4, just include the other points also, though just the similarity data is like depends on the k values. That is why we say that in k nearest neighbor, the parameter that we need to change in order to find or in order to improve the performances, just change the k value. You can try by changing the k value. You can start from maybe k is equal to 1 and then 2 and then 3 and 4 until you find the best performance. So by changing the k values, we can improve the performance. That means it depends on the k value, the value or the performance, it can be different. So when k value is 3 and when k value is 2, the performance and the accuracy may be different. So because of that one, in order to improve the performance in k nearest neighbor algorithms, just change the k value and then it's try to check, and then you can see that the performance, and keep going until you can achieve the best performance. This is the one mechanism or one example of k nearest neighbors for classification. For example, this one is just 2, k is equal to like votes for that one also. So it's selecting for this one also when the number of the 2 votes for the cat, and when the number is like increasing, what each for buffalo and the lion and that one. So based on this one, the cat can be the winner one. So just based on the similarity or based on the 2 votes, this one can be the winner one based on the similarity. The other one, one example of the classification or classified algorithm is the support vector machine or SVM. This one is also, I think, the algorithm that mostly used for classification also. That's support vector machine or SVM. Support vector machine is also one type of classifier that try to maximize the margin between different data points and the classification boundary. So this is this type of algorithm, the support vector machine algorithm, is type of algorithm that can be used to learn both the linear and the non-linear data. We say that in classification, there are 2 way of classification, or based on the data natures. Maybe the data is like classifier. We can say that this one, and maybe the split one is like this one. So some of the data will be like this one. This is one class, and another one is maybe like this one. So this one is, we can say that the linear one. Another one is the nonlinear one. We say that in nonlinear one, the data nature based on the data nature, maybe the split is like this one. So the one data is here, and the another data is, or another class is like that one. So in order to split that one, this line is, or the support vector line is, should be non-parallel. That's called nonlinear. So this type of way is like, we can say that nonlinear. So this support vector machine is a new classification method for both linear and the nonlinear data. That is why actually this one is also a good algorithm to classify in both type of data. So by using this linear and nonlinear mapping to transfer the original data into the higher dimension. For example, this one, there is the data here, one class here, another class here, and split this one by using these lines, or we can say that hyperplane. So by increasing or maximizing this margin width between this data and this data, that means when the margin between this data is like wide, that means that the better performance. That is, we say that support vector machine working principle. So as shown in this one, how to find the best decision boundary in support vector machine. The one is like all lines in the figure is correctly separate the 2 classes. For example, in this one is like there is 2 class here, just a binary class. The one class is the circle one and the one is rectangle one. So in order to separate correctly these classes, there are different ways of hyperplanes here. The one is like we use this one, another one is this line, another one is this line. So there are different possibilities, but finally we should be select that the one that is best fits with to separate the one that have a maximized margin or widest margin. So in order to select this one, from this one, from this one, or from this one, which lines that separate the two classes with the big margin. The margin means the distance between this one and this one. So to draw that one, we can calculate, or we can select based on the margins. With an appropriate nonlinear mapping to sufficiently high dimension, data from two classes can always be separated by hyperplane. Hyperplane means this line is, we can say, hyperplane, or this possibilities we can say that hyperplane. So the SVM finds this hyperplane using the support vectors. Support vector is like we say that this point and this point, that means the final points that used to separate from the other classes, we can say that support vector. So for this class, this point and this point is the last point, which is closest to this one for drawing this line. And from this class, this point or this dot is, it showed that the support vector that used to separate or make the hyperplanes. So these points and this point, we can say that support vectors. So in order to draw the hyperplanes, we should be consider that, and we can identify the hyperplanes, the support vectors, and then we can put the hyperplane. So the way to draw the hyperplane, it determines the classification performance. So the hyperplanes and the margins, that's margin and the hyperplane based on this line. The line that is farthest from all training examples will have a better generalization capabilities. That means farthest from all training example means like the margin between, or the widest between this one and this one, if it become wide, the generalization performance or the accuracy, the precision and the recall performance will be better. So the objective of this SVM is to try to maximize the margin between the points. So like for example here general property, that's the general philosophy of SVM algorithm is try to maximize the margin that the chance the classification will be correct on the new data. So this is just based on this one. There is a different way of planes like this. In order to classify this one, this is the last support vector to make this hyperplane, and this one is the last point in this class to draw the hyperplane. So based on this one, actually this class is like correctly defined based on that one. You see small margin. So like this is the same data but like different margins. So in this case it's like the margin between the 2 points is like, because of just we select like this type of lines, the margin between the two is small. When it comes to in this one, instead of just only picking this one, so the line is just draw like this one, and this one is the line is draw like this one, then the margin between this one and this one, it becomes wide. So that means based on that definition, when the margin between the two data points is high, the classification accuracy will be increased. So from this one and from this one, the second one or this one have the better performance than the previous one, because in this case the margin between the 2 points will be high, that maximize the margin between the two. Yeah, this support vectors means just this one is the last data point which is nearest to this hyperplane, and this one also the last data point which is nearest to this one. So that means these data points, we can say that support vector that helps to draw the hyperplane. In this case, this line, this point and this point is nearest to this hyperplanes to draw the hyperplane. So like these support vectors can help us to draw the hyperplane, or in order to separate between the two data points, that is we say that support vector, and the name indicates support vector machine means just like the draw or the hyperplane is based on the support vectors. So the same case in this one, just the data is because of his supervised data is pre-processed like this one, x1 and y1, x and y. Then x is the set of training tuples associated with the class label y. So y is the target and x is the input features or tuples. So in order to determine the class label y, based on this type of margins, just determine that in which class that class label will be determines. So this SVM searches for the hyperplane with the largest margin, the maximum margin hyperplane. Just this is the task. So this is our data. We have two class. Let's say, for example, in this one class of data, and this is another class of data. So our goal is find the linear decision boundary or hyperplane that separate the class. So in order to separate this class, can we draw this one just like maybe which one is like the better ways to select the one. So the one possible solution is like just draw by this one. So separate this one from here, and another solution is maybe we can just select like this one, another possible solution. So the first one is like this one, and the second one is like this one, and also another possible, like this is all the possible solutions, the possible hyperplanes to separate the two classes. But from this type of options, we need to decide that which one is like the best one. So in SVM algorithms, just when we just adjust the parameters, select the best one and then define the performance. So in the coding system, actually no need to manually assign that one, but we need to just adjust the parameters in order to select the best hyperplanes and then determine based on that one. So from this one, we just consider that which hyperplanes will be the best one based on the margins. So from this one and this one, for example, which one is the better? Whether that B1, the one this hyperplane, and the other one is the B2. So how do we define which is the better? So based on our discussion, we say that when we just draw the hyperplane, we should be considered that there is a big margin between the two data points. So based on that concept, from these two hyperplanes, which do you think that better, that B1 or a B2? And then if you say that B1, it's Y, and if you say B2, just try to put your reasons on this one. So from this one, just the data point is like just considering between that one, like this one. So the one is the B2 is like this one, and the B1 is like this one. So the margin, or in order to identify the support vectors, we can just make it this one is different from this one, or in order to calculate the margin, first we should be just indicate that the support vectors here. And for this line, the support vector, because this is the last data point which is nearest to that one, so we should be use this one as a support vector and draw these lines. For this one also, because this point is nearest to this line, so we should be select this line, and then we can draw based on this one. Actually the margin between this one and this one is very narrow, but here the margin is big. So based on this one, the hyperplane that maximize the margin will have a better generalization. So based on this, like B1 is better than the B2, because just the margin between these two is like wider than that one. So the first one, just draw a line and then pick the support vectors in order to calculate the margin between that points, and then we can decide that the last or the big or the highest margin have the better performance. So based on that one, we can say that in this case the B1 is better than B2. So now we have a test sample. In this case we have a test sample. The read one is a test sample. So based on this one, the test sample actually, if like lying in these classes, that means the test sample can be classified into this one, because just now is highly separated by using the margins or maximize the margins, and then after that when we give the test sample, just pick that one. So based on this one, it can be easily the test sample is categorized into these rectangle classes. So in SVM, also the main goal or objective is just want to maximize the margin. So that margin is actually just defined by 2 over W, which is equivalent to minimizing the W over 2 square over 2. That is determined actually. Here there is that determine the W1, or in this case we say that the point from this one to this one, we can say the W, and also the big one, and which is this is equal to, because this one is the main line, we say that this one W times X and B is equal to 0. So that's determined for this one. So this equation is like coming from this one, the margin 2 over W. So this indicating that the one, or the main line, is like indicating this one width. So the main objective is like in order to the margin 2 over W, because just separate into 2. So based on this equation, if the margin can be maximized, that means the performance will be increasing. So this is the first class. That is why the line that indicates like the weight and X data and bias and then 0. And this one is actually because the other classes, which is say that -1 in the other, and this one is in the other classes. So we can say that the +1 this. So based on this one, we can just determine that the +1, the class will be a +1 if this one is greater than 1, and the class to the -1 if the less than or equal to -1. Just determine on that one. This is the hyperplane, the main hyperplane, and then we can say we can just check that whether the class is in this class or in this class by calculating on this one in SVM equations, and then the final goal is just maximize the margin on this one. As the conclusion for classification algorithms, this SVM is used for both classification and as well as for a prediction also. So maybe in SVM there are different parameters that we need to assign. So in the support vector classification, we can tune or change different parameters. So this SVC or support vector classifier, like this one for example, the class is like SVC or support vector classifier, and there are different parameters like regularization. The kernel is like the default one is RBF, and the default of the regularization is 1, and there is a degree here, the gamma, and different parameters that one. So let's see this one. So in order to implement the support vector classification, there are different parameters that we need to adjust in order to improve the performance. So we can just try, for example, by changing the parameter, and we can see the accuracy, the precision, and the recall. And then if the performance still is not improved, and then again change other parameters, and we can see that until we get like the best performance. So from these parameters, the one parameter that we need to arrange or tune in the classification is like regularization. This regularization, actually the value is a float, and the default value in the regularization is 1. So that means if we didn't assign any value for the C value, by default the algorithm uses the C value or the regularization value as 1.0. So this regularization parameter, the strength of the regularization is inversely proportional to C. So this regularization actually that controls the overfitting one. So based on this value, just assign. So the value is maybe 1, maybe 1 point something, or like 5, 10.0, like that one. So by changing these parameters, we can just see and check the performance. So the one parameter, the most common one, is this one. Another parameter that we need to change in during the training is the kernel. This kernel actually that indicated that how to just separate that hyperplanes between different data points. So the value that we need to change in the kernel is like, the kernel is maybe like type of linear lines, and maybe polynomial lines, radial base function lines, maybe sigmoid lines, and pre-computed lines. So this is different options. So when you change this value or the kernel value, that means the performance of the SVC classification or the support vector machine classification result will be different. In this SVM, if we didn't assign any linear value here, the default one is become radial based functions. Radial, that means like if we didn't give any value for a kernel value, that means the final value it become, the default value it become radial based function. So this specifies the kernel type to used in the algorithms. If none is given, RBF will be used by default. If equal label is given, it is used to pre-compute the kernel matrix from the data matrix. That matrix should be an array of the shape like putting like this number of samples. So by changing the kernels here, linear, polynomial, RBF and sigmoid, we can just see that which one is the best one or which achieves the best performance. So maybe we can combine. Once we can select, just change the regularization or C value and the kernel value, and then by combining this one just until we get the best accuracy or precision and recall, just we can try to tune the parameters. The other one, degree of the polynomial kernel functions. So the default one, the value is integer and the default value is 3, but we can change this one. So this value must be non-negative value, so we should be just greater than or equal to like the 1, 2, 3 and like that one. So by assigning this degree, also we can increase the performance of the algorithms. Another one is the gamma value. So just the type of the value is scale or auto. So the default one, or also there is a float, but the default one will be the scale. So the kernel coefficient for RBF, polynomial and sigmoid, we can assign like this value. So by using different scale values in the gamma, we can just try to improve the performance on that in this case. There is also the other parameters like coefficient, shrinking, probability, total, cache size, class weight, and it's too much, but the most common that determine the value one is this 3 is like the major one, like the regularization, the kernel, the degree, and the gamma is the parameter that needs to tune in order to achieve the parameter. So in detail, actually from this skill-learn library, you can just check it by each parameters and you can read more further about each parameters in detail. But now just in order to highlight that some of the common parameters that we need to tune or change until we get the better performances, you try to adjust this type of parameters, and then also you can just check like the other parameters in detail about that one. Actually in this skill libraries, not only for this algorithms, you can just try to search different algorithms on this one, and you can see that what type of parameters we need to adjust on there, what type of parameters we need to change, and then how then for example what is the purpose of each parameters in order to improve the performance. So this just the highlight one that's about the parameters that we need to adjust in SVM algorithm. Okay, I think just in order to show some highlight about the simple codes and examples about the SVM, I need to show that different code that show that how to just the classification algorithm. It looks like this one. So this is just a sample code about the SVM classifier. So the Python code that showed that, for example, the first one is the library. So this is a Python have a different open source libraries. So we can call it a different library from this one. So from this one, for example, there is a pandas that is used to read the data set, and then like this seaborn is like for plotting the data into different ways, and the matplot, this plot library is also for plotting the data into different ways. And then the library for confusion matrix classification report, ROC value, and the accuracy is used to calculate the performance of the classification algorithm. And then there is the load the data set. So because when we just consider that loading the data set here, so we can read like this one is a sample, the data set that is the iris data, and the data it looks like this one. So we can just pre-process the data, and we can see that first we can check that whether there is a null value or missing value or not. So when you're checking that one, there is no null value, you say that here all the data is no null value, that means no missing value. Also we can check if there is a missing value. So in all data there is no missing value, because we say that in the data pre-processing part, the first step we should be what? Fill or avoid the missing value. So in order to check that one, we can see this one, and if there is missing value we can adjust like this one. Then just this one is a descriptive statics, like by say df describe, we can say that the total the data and the features on this one, and then say the count and the mean the standard deviation, just count like that one. So this is just based on this one, the data has 3 different classes. You see this one, the data, because this read the iris data, this one is the loading the data. And when you say that df.head, we can see that the data here. So the attribute spatial length, spatial width, petal length, petal width, and spatials all show that this one is the data. It looks like this one. So spatial length, spatial width, petal length, and petal width show that the tuples or the features of the data. And this species is like the class name, the class label. So in the class, this is the one data actually, because it's like not displayed here, but the total class type is different, depends. So this is the class 1, the value like iris, stosa, iris with color, Virginia, and the 3 different class here. It shows that. So for the one class, total is 15 data. For the other class, also total of 50 data, and for the other one, a total of 50 data. So it shows that this one is the total data is like 50, 50, 50. So the total amount of data is 150 from each classes. So 3 different class of flowers. When we plot this one, also plotting like this one, we can see that this is a plot. So by using scatter plots, we can just x value is the spatial length and y value is spatial width, and then here is like species, which is the class name. Based on spatial length is spatial width, the data is plotting like this one. And also based on petal length and petal width, the class is just like plotting like this one. Because in the data there are different features, right? We say that here, spatial length, spatial width, petal length, petal width. So first just plotting based on these 2 parameters, and second plot like by using these 2 parameters. So for this one and this one, have a species or a class for this one, like this one. So this is, after that one, there is a pre-processing data normalization one. So to process that one, just changing the value into the 0 and 1 formats, and then the second one is split the training data and target data to that one. So X is assigned like the training data, and Y is the target data for in this case. For X, we can say that df.drop column and species means we can drop the column and species, which indicates the class label, and then we can say that this one is training data. After dropping the species column from the table, that one, so the data that is except the species one is like we say that training data, and the Y is indicating that only the species columns, that is called the target data or the class labels. And after that one, we can make it like min-max scaler. This min-max scaler is like a data pre-processing that changing into the data, into the format, into the 0 and 1. So we can fit that data and transform into the data which is more fitting into the algorithms. Then actually just this one is for the highlights. Maybe there is a real practical lab. So this is as highlights for the in order to show that the example for the different classification algorithms, but in more detail we can see that practically in the lab. So just today for us the highlight how it looks like this one, the parameters in KNN and SVM. And then we can say that just splitting the data into test data and training data, because in order to measure the performance, for example, we can split the training and test data like this one. There is X train, X test, Y train, Y test, and the train split is like 0.2 is for testing. That means 20% of the data should be kept for testing data, and 80%, the remaining 80% of the data is assigned for the training and the testing data. So this X train, X test, Y train, Y test is like X train and Y train is for training, and X test and Y test is kept for the testing data. So just the training and the test data is splitting by using this code. And then after just pre-processing this one, so the step for this one is actually the data pre-processing part, which is almost common for the different algorithms. So until this one, maybe the data pre-processing part is similar for KNN, for SVM, and for other algorithms. So the next part, we can choose the model. Let's say, for example, first I just pick KNN model. So in KNN model, just we can call it the library from this one, from the skiller. We can import like the k-nearest neighbor classifier, this algorithm, from the library. And then in order to calculate the performance, we can just call it the confusion matrix and the accuracy score, because this is the performance measurement parameters. And also there is cross validation. And then classifier is equal to k-nearest neighbor classifier, and neighbor is equal to 3. That means the k value in this case is equal to 3. So we assign, we say that the main parameter in KNN is just 3. I mean, k value is the main parameter in KNN model. So just we can assign that the k value here, and we can say that k is equal to 3. And then we can classifier is equal to, because we say that we assign the classifier the model, the KNN model here, classifier is equal to this name, actually just the name that we assign. So we can change this name as another one. We can say also KNN here. So classifier dot fit, in order to fitting the model, classifier dot fit X train and the Y train. So X train, Y train is for training, and then from this split, X test and Y test is keeping for testing with the 20% of the data. So for training only we use the X train and the Y train value. Then to predict, then now already train the model, the KNN model is already trained. So in order to test the data, we say that then predict or classify the data. Pred1 is equal to classifier, this algorithm, dot predict, and then case test. Already this classifier is the trained algorithm, dot predict X test. So X test indicates that the 20% of the data that is kept for testing the performance of the model. And then it showed that means this is the result, because the class is assigned like 0, 1, 2, 3 different class for the different flowers. 3 different class, that is why 1 indicating the 1, 0, and 2, and then 1. So because 20% of the data from 150%, 20% means like 1, 2, 3, 4, 5, 6, and it's too much. So the prediction. And the actual value is Y test. So in order to calculate the accuracy, the precision, the recall, the model compare this result, the prediction result, and the actual result. So this is the actual, means that we already defined, or the ground truth. And the predicted one is show that the predicted result that is predicted or classified by the proposed KNN model. So when compare this result and compare this result, we can evaluate the performance of the model. So in order to calculate the accuracy square is the evaluation between Y test and the pred1, because pred1 is the prediction result or the classification result here, saved here. So based on this one, the accuracy of the KNN model is become 1, which is means 100%. And then in order to show that the confusion matrix, also we can draw the confusion matrix by using confusion matrix Y test and pred1. That means the actual and the prediction one. And then we can see that different classes, and then all like show that correctly classified class. This is called the confusion matrix. In the classification report, it showed that the precision, recall, F1 score, performance measure is so for iris tosa, the precision is 1, recall is 1, F1 score, that is 100%. That means all the data is accurately classified. For this data also, the precision is 1, 100%, 100%, 100%. So the total data, test data for this one is 10. The total data is 9. So all 9 data is already correctly classified on this one. So if the actual and the predicted class is exactly the same, that means the accuracy is 100%, the precision is 100%, and the recall and the F1 square become 100%. So this one from this class, the test data that we use is like 11. So the total one is around the 13 data is used for us test data. So the total data for testing the data is 30. So all the data show that 100%. This is just the sample one. Another is in SVM or support vector machine. Actually, the data pre-processing is the same like the KNA. So we only consider that only on the algorithm parts. So when we come into the SVM part, we can just develop the model. So we can call it the algorithm SVC or support vector classifier from the library. So from scalar.svm import SVC. So we can import the algorithm classifier of SVC or support vector classifier. Then we can just save the model as SVM model is equal to SVC. This one is just indicating the name for this classifier. Then we can just train the model, SVM model, because we say the model name here, dot fit X train Y train. This X train and Y train is the same with the above one, the data processing that takes, because I already used the same data processing, so no need to repeat again. Just we can use this, all the data pre-processing is like the same with like the KNN. So this is just in general. So the accuracy shows that also 100% for SVM. In case if the accuracy score is like poor, or if the performance is not good, we can tune different parameters in support vector machine. The first one is regularization or C value. So we can say that, for example, in this case, just SVC and then no value here. That means just using the default value. In this case, C is equal to 1, and then maybe the scale, the gamma value, and also the kernel value is RBF. Because if we didn't assign any value in this one, that means just using the default parameters. But if we just assign like this one, SVM model is equal to SVC, C is equal to 10. If we just assign like this one, that means the regularization performance is 10. Then when you predict and train, and when the performance is still 100%. When the C value is 0.0%, you see, for example, when we make it C or the regularization performance 0.01, the score become 30%, which is very poor performance. So the value, this changing this regularization performance can affect the performance of the model. So changing like that one. Another parameter is the gamma. Gamma is equal to 5. So SVM model dot fit X train and Y train. So just the default one is actually here auto, but we can just also assign that this one is 5 and like that one, and we can see the accuracy here. And the kernel also, the default is actually radial base function or RBF, but we can say SVM kernel is equal to linear, and we can just see the performance. Or we can say the kernel into RBF, and the performance is still 1. When the kernel is polynomial, the performance also become like this one. When the kernel become sigmoid, the performance is become 0.3, which is, so based on this case, maybe sigmoid is not good. So, and then the other one, it showed that the same performance, so we can pick it, the 1. So this is just the way how to choose the parameters in order to achieve, or in order to increase the accuracy of the model. So based on this one, we can just choose all the best parameters based on this one. So the final model we can choose based on the above one. We can say finally, just we can use this type of models. SVM model, SVC, kernel is equal to RBF, because RBF based on this one is achieve 100%. So just I pick this one. This and the polynomial, RBF and linear is almost the same. So for this case, just I will pick RBF. The gamma value, C is equal to 10 is achieve better than the other one. So gamma like 5 and 10, the same performance, so like based on this one. So when you train that one, and the performance it become 100%. And then after that we can draw the confusion matrix, and we can say that the performance in the classification report. In the classification report, like the same as KNN, the precision recall and F1 score of the SVM is calculated, and we can see that the accuracy, the precision, the recall, the F1 score for all the test data is become 100%. So this is the way how to just do this one. So just this, in order to integrate how like the theoretical and the practical part, it looks like that one. But in our situations, just we can practice this one in the lab for each line of the code, and we will see more detail in the class. So this is like a little introduction and what type of parameters we should be changing the coding part of like different classification algorithms. So decision tree also the same, but we need to we didn't go in detail for this one. So maybe just we will see in the lab part, and also maybe just refer from the manual one. Okay, so today about this one, we already highlight about the classification parts. We already see and summarize about different classification algorithms, and we need to highlight on this one. So in the next part, I think about the regression part, we already see that the difference from regression and classification is in the regression part, just only focus for continuous values, So this regression means, for example, when we need to predict one specific value, or we cannot just like, if the data nature is not categorical, so we need to use like different type of regression algorithms like logistic regression, linear regression, and other type of regression algorithms for the prediction one. So I think it's just better to just refer this one and read more about this one, and because already like I already highlight that what is the difference between classification and regression. So for now we didn't go in detail for regression, and in the next part I will try to highlight about how we can apply this machine learning for the optical communication and sensor networks. Okay, thank you.